Lab 3 Black Hole Mass Objectives. Find a black hole mass using Newton's law of universal gravitation, the results from our given data, and analysis of the given data. Discuss lab elaboration. Use Python to make a model about the star's orbit around the black hole. Answer questions. We have our data, that is the Excel file that Web of Science gave us, giving the x and y position, the orbit from a star around a black hole. The star mass, which is 4.33819 E27, time step delta t, which is equal to 86,400 seconds, 1 Earth day. The black hole position, that is 0, -2 e plus 10, 0, and the constant g, which is equal to 6.67 e minus 11. With all these and the Newton law of universal gravitation, we're going to find m2. Well, you know, we have the law of universal gravitation, which is F net equal g m1 m2 over r square. We then clear the equation just for having m2 equals something, which is m2 equal the magnitude of F net times r square over gm1. And how we're going to know r, which is using the Pythagorean theorem, r square equal r or r2 square minus r1 square. And well, we can write f net 2 like the changing momentum over changing time, delta p over delta t. And we know that when delta t is really small, f net will be equal to the momentum principle, right? Well, so here I grab all the information I just told you, and I make my model in Python. I have my mass, I have delta t, got the time, well, the initial time is 0, and I got here for it to open me to use the Excel file is stardata.csv. I have it here. Here is it. Well, and well, I'm gonna need to calculate the component x and y component of the velocity, which here I have the formula. I'm gonna need this index. Here's this is the calculation. We didn't have that. Well, this is gonna happen. Well, index is less than length x minus 1. The initial velocity is equal to the vector x velocity index minus 1, comma y velocity index minus 1, comma 0, and the b final is vector x velocity index minus y velocity index, comma 0. We have that initial momentum is star mass initial velocity, right? And final momentum will be star mass times initial final velocity. We need to know our delta v and delta p. Delta v is final velocity minus initial velocity, and delta p is final momentum minus initial momentum. Well, dPdt I right here is equal to f net, and dPdt is equal to delta p over the delta t, changing momentum over changing time. The p hat, which is the p hat of the f net, will be, well, the momentum will be initial momentum over the magnitude of the initial momentum. The magnitude of dPdt, or the magnitude of f net, would be equal to the magnitude of the final momentum minus the magnitude of the initial momentum over the delta t, which is the magnitude, this thing here up is the delta p. And the parallel dPdt, which is the parallel dPdt, is the magnitude of dPdt times the p hat. The parallel f net is equal to dPdt parallel. We have it here. The perpendicular dPdt, which is perpendicular f net, is equal to dPdt minus dPdt parallel. We then have our constant g, which is equal to 6.67 e minus 11. We have here our Pythagorean, well, no, we have here finding the distance, right? Pythagorean theorem. and the whole black hole mass, which is the magnitude of S net times distance to the square over star mass times the constant g. Well, let's kill the arrows. And as I want to know the black hole mass, my well, in the my model will tell me at the end, well, in the shell, what's the black hole mass, because I'm telling it to print it. So let's run the model. Oh, yeah, you see it there, right? Yes, that's mine. Here I have 2.567589796 2 E31 is my black hole mass. So let's see if it's correct. I have it up here, and let's see. Yes, 2.567 E31 is correct. Well, so I made my model. It's good. Now let's pass to the next part. It's answering the questions. What does it mean that how this the three F nets is not equal from this? Well, F net is not always gonna be the change over the change of momentum over the change of time. Well, you know, F net can be written in many forms, so that's how it's different. It's I have it here. No, F net is the gm1 m2 over r squared, but it is to we have to that F net is equal to delta p over delta t. So delta p over the delta t will always be F net, but F net is not always gonna be delta p over delta t. So next question. What if? Imagine the black hole whose mass you found was removed, and a different black hole was placed in the same location. Assume the motion of the observed star remains unchanged, and is affected only by the gravitational force of the new black hole. Could you tell the difference? In other words, is it possible for you to find a value for the mass of the new black hole that is different from the mass you found for the original one? Well, like we have that is the same star moving around. It's the same star. That means that the star mass can change. So as we have here in our equation, that m2 uh, varies from m1, and m1 can change, and it will have the same velocity. That means m2 will be the same, right? So that's my video.